What if I told you that time travel has already happened, not in science fiction, but in space? A Russian cosmonaut spent more than 2 years orbiting Earth and returned younger by a fraction of a second compared to all of us on the ground. It sounds impossible, but it's measurable, proven, and woven into our everyday technology. The real question isn't, is time travel possible? It's how far we could push it if we had the speed, the energy, and the technology. The astronaut who bent time high above the planet, a single human circles again and again, their home a narrow capsule, their horizon a blue curve fading into black. To those of us watching from Earth, each orbit seems routine, day, night, sunrise, sunset, a repeating cycle. But inside that small outpost, something subtle unfolds. The body's inner clock, the beating heart and dividing cells, is sliding ever so slightly out of sync with ours. The difference is invisible to the eye, but it builds with each trip around the globe. By the time the mission is finished, that astronaut has carried back a piece of the future, written not in memories, but in minutes and fractions of seconds. This is not a trick of fatigue or a symptom of long days spent locked in metal. It is the physics of motion. When you move close to orbital speeds, the fabric of time itself changes its rate. Every tick of an onboard clock is stretched, compared with one that rests down here. It feels natural to believe that a second is the same everywhere, in every place, for every person. Our lived experience reinforces this intuition. Two people shake hands, toss a ball, or pause to breathe, all apparently sharing the same flow. Yet when nature's stopwatch is carefully measured across different states of motion, the sameness dissolves. The astronaut who circled Earth for over 800 days carried a clock within their body that drifted imperceptibly behind ours. On returning home, they were younger than those who stayed. The difference sounds tiny, 0.02 of a second. Against the sweep of a lifetime, this is negligible, smaller than the blink of an eye. But what matters is not its size. What matters is that this was not imagined. Instruments tracked it to the microsecond, confirming that living tissue can slip into the future a little faster than its peers. Think of two watches. You take them from the same box, set them together to the same time, and start them ticking. Place one watch on the table, the other on a wheel spinning at tremendous speed. When you check them together again later, they no longer agree. The difference may not bother an everyday schedule, but it gives away a secret. The wheel has changed the flow of time for the moving watch. Our orbiting traveler was that moving watch carrying skin, bone, and thought through a clockwork adjusted by motion. This is the greatest human time traveler so far. Not a jumper with a device strapped to their wrist, not a character in a story. A real person whose lifetime has parted ways with ours by a measurable slice. Their return younger than expected serves as proof. Time is not a background wall. It can be bent, slowed, stretched. The astronauts circling Earth every day, whether for months or years, enact the same principle. Their clocks, both mechanical and biological, shift slightly away from those down here. They do not notice it. You would not notice it. But the instruments in laboratories and the coded equations and navigation satellites record the drift with relentless precision. When you think of time travel, you might picture a grand machine spinning gears and glowing with power before throwing someone into past or future. Instead, the actual journey begins far more quietly. We ride on it already every second. Time dilation in orbit is time travel in reality. The astronaut is not hurled across centuries, but they arrive at our present a little fresher, as though they skipped some beats. The rest of us endured. The result was checked and confirmed many times. It is difficult for the mind to accept because our senses give no clue. From the astronaut's perspective inside the capsule, nothing feels slower. Meals are eaten, notes are written, moments pass as always. On Earth, days flip through calendars without break. Only when two clocks are brought together does the hidden difference reveal itself. That is how we know. Physics recorded it, not imagination. This achievement reframes what time travel means. We do not have to wait for fictional breakthroughs. It has been performed using nothing more than speed and patience. The astronaut story is a constant reminder that even human-scale journeys already bend the timeline. The irony is that it took enormous effort to show us something so subtle. Thousands of orbits and hundreds of days in space yielded a difference that vanishes if you blink. Yet contained in that sliver is a gateway to understanding. You and I often treat time as something absolute. We carry watches, phones, calendars, all assuming they share one master rhythm. The astronaut's journey tells us that is wrong. Multiple rhythms coexist, each tuned to motion and position in gravity. Our everyday sense is parochial, built on speeds too slow and fields too even to reveal the discrepancies. But when people push into space and circle the Earth at thousands of meters per second, the veil comes down. What strikes scientists is how consistent the physics has proven. The predictions made on paper have matched the readings in orbit. The principle is not speculation. It is encoded into our technologies, checked on every mission, tracked with atomic precision. The astronaut's younger return is not an anecdote, but a checkpoint on a curve traced by equations that repeat in labs and satellites. Every step confirms that time is flexible. This beginning matters because it lays down the foundation. Time travel is not merely a dream, it is already occurring, inch by inch, second by second, confirmed by living people. Our fascination with ancient tales of slipping into another age finds its quiet counterpart in a traveler orbiting 803 days above Earth, arriving home with a clock out of joint. It may seem modest, but conceptually it is revolutionary. It proves that the door is open, that physics already allows people to step forward into time at slightly different angles. So when we speak of time machines, remember that one already exists, the act of flying fast. The astronaut has given us living testimony that motion alone reshapes the river we all drift down. That should transform how we think about the subject. If forward motion can leave us younger by 0.02 seconds in a couple of years, what might faster paths achieve? Could decades be skipped in the span of days? Could journeys near light speed let a person touch the year 10,000, while their own body barely records age? The imagination strains, but the seed has germinated in real events. From the start, then, we have proof. Time travel is not philosophy, not fancy, but demonstrated fact. That leaves us with a larger problem. If the flow of time flexes in the presence of speed, when did we first realize time was not absolute? How did science uncover this strange plasticity? To answer, we must step back more than a century to a pair of mirrors and a beam of light in the 1880s. The experiment that broke time. What if you fired a beam of light across the Earth while the planet itself was racing around the sun? Would the light's pace shift depending on which way you aimed it? Common sense tells us it should. If you move into the wind, you feel extra push, and with the wind, you feel carried along. Shouldn't light act the same way? That was the expectation more than a century ago, when the search for answers about the nature of space seemed close to resolution. Instead, what followed was an unexpected failure that cracked the foundation of physics and forced us to rethink time itself. In that era, scientists believed light had to ripple through some hidden medium. They called it ether, an invisible fabric filling all of space. Just as sound travels through air and water waves travel across the ocean, light was thought to need its own carrier. When the Earth moved, it should sweep through that ether, and beams of light should reveal speed differences depending on direction. Catching this effect was the goal, and an ingenious device made of mirrors was designed to reveal even the smallest change. This instrument split one beam into two, sending each along paths at right angles. By recombining them, patterns of bright and dark fringes appeared, like ripples overlapping. If one path took slightly longer because the planet was moving into the ether in that direction, the patterns would shift and prove the medium existed. On paper, the prediction looked clear. Light should behave like a runner on a moving walkway. Fighting against the belt slows them down, while moving with it grants a boost. But when the results came back, something remarkable appeared. No matter the direction, the combined beams matched perfectly. The bright and dark fringes remained steady, without drift or delay. It was as though the walkway didn't exist, or the runner somehow kept exactly the same pace no matter which way they ran. The ether could not be found, and the expectation that light would change speed relative to Earth's motion collapsed. This absence was not a small discrepancy. The setup was sensitive enough to detect changes far smaller than the width of a hair, and still nothing moved. To the experimenters, it was baffling. Were the instruments flawed, or was the whole idea of ether mistaken? The Earth kept revolving at tremendous speed, yet light ignored it completely. Think of standing in a storm, running first into gusts and then with them. You should feel a shift. But this beam of light, and every attempt to repeat the test, refused to bend to that logic. Imagine trying over and discovering that no matter which way you ran, the wind pressed against you with equal force. That was the unsettling reality. Their device was designed to succeed. Instead, its failure revealed something deeper. The universe was not operating on Newton's sense of absolute motion. If the ether was gone and light remained unwavering, then time and space themselves had to shoulder the task of adjusting. This simple negative result, instead of sliding into obscurity, became a cornerstone moment. From that point forward, thinkers recognized that a choice had to be made. Either light disobeyed rules other waves followed, or the rules of motion, distance, and time themselves were different from what anyone expected. It wasn't only the numbers that forced the issue. The sheer stubbornness of light's speed carried meaning. If nothing altered it, then the structures of measurement wrapped around it had to do the altering. You can see why this confused and frustrated people. The machinery was beautiful, the idea straightforward, and yet no effect appeared. Their aim was to confirm an old assumption, but what they built instead was a doorway into a new view of nature. When the puzzle pieces refused to fit, the conclusion became unavoidable. Our picture of time and space required rewriting. The analogy to weather is powerful because it captures the feeling of contradiction. If you've ever sailed, you know the direction of wind decides your pace. But with light, it was as though every sail caught the same push regardless of heading. No more hidden current, no more medium behind the scenes. Instead, something stranger at play, something resisting all attempts at detection. This is one of those moments where failure becomes priceless. A setup carefully crafted to validate belief instead destroyed it. If you imagine science as a map, here was a place where explorers expected to chart simple coastline. Instead, they found a cavern leading far underground. The path forward became less obvious, but more profound. Without intending it, they had destabilized the solid ground of Newton's universe. What gives this story its weight is that the results did not vanish into doubt or dismissal. They were precise, replicable, and stubborn. Repeated efforts around the world kept showing the same thing. The speed of light was immune to the Earth's motion. The more these experiments failed to see a shift, the more it became clear the foundation of space and time must be built differently. It is unusual that a null result, finding nothing at all, becomes one of the most famous discoveries. Yet here, the failure mattered more than any success could have. What people expected was a medium that reassured them physics worked the same way it always had. What they found instead was that physics required a revolution. Nothing less could account for light's refusal to play along. By ignoring the ether and holding steady across directions, light had sent a message. It said, "The universe doesn't care about your moving frame. The constant isn't your watch or your ruler. It's me. If I stay fixed, then your watch and your ruler must bend." That idea still lay ahead, waiting for someone bold enough to say it outright. The world had reached an impasse. To cling to old rules meant denying clear data. To follow the evidence meant surrendering even the idea of absolute time, something no one had ever dared before. The stage was set for a new perspective, but it required an audacious step, a willingness to trade intuition for consistency and to let the constancy of light dictate the nature of reality. Out of that readiness emerged a theory that no observer could outrun or chase light. The implication would be staggering, that simultaneity itself was relative, that clocks could tick at different rates depending on motion, and that time travel of a kind was possible. These ideas were shocking, but they made sense of the stubborn failure that had baffled experimenters. The simple question, shouldn't light move faster or slower as Earth races around its orbit, turned out to open a far larger story. Time itself was no longer absolute. Space was no longer rigid, all because a pair of light beams refused to budge from their pattern. The null result spoke volumes, and its echo shook every assumption that came before. And now enters a young thinker who chose to accept what the experiment had told the world, that the problem was not light, but time. That thinker was Einstein, and his vision would turn this failed expectation into one of the greatest breakthroughs of all. Einstein's great twist. What if the speed of light never changes no matter what you do, and instead it's time itself that bends to make that rule work? That was the twist proposed in 1905, and it forced people to abandon the idea of time as a single universal river. Until then, most of the world assumed that clocks everywhere ticked in step. Noon was the same for you as it was for me, separated only by distance. The heartbeat of the universe was thought to be common and absolute. But if light's pace was fixed, that assumption had to go. Time itself had to gain flexibility. So imagine this daring claim. No matter how fast you move, you cannot catch up to light. If you sprint alongside a ray, you still measure it racing past at the same speed. If you shine a torch while on a moving train, the beam doesn't add your train's motion on top. It remains identical to what someone watching from the ground would see. That sounds simple, but when you play it out, the result is radical. It means that notions of simultaneity, of two events happening at the same time, are more fragile than we once thought. We can make this less abstract with a small example. Picture two friends clapping in rhythm. At rest, their hands meet in sync. One begins walking quickly, while the other remains still. The moving friend now measures the timing differently, slightly shifted from the point of view of the one who stands. Their rhythms no longer line up in a common beat. What holds true for clapping holds true for everything. Motion changes how moments are arranged. In this sense, the steady beat of the universe splits, depending on movement. To understand this better, try the classic image of a train. Inside the carriage, a passenger switches on a light that bounces up and down between the ceiling and floor. To them, the beam travels straight up and down, taking the same time with every bounce. But to an observer standing outside, the train races forward as the light bounces. What that observer sees is a diagonal zigzag. The light not only rises and falls, but also slides along the train's path. The longer distance means it must take longer to complete each bounce. Yet both people must still agree on the speed of light. So how can the passenger and the observer reconcile this? The only option is that each measures a different tick of time itself. For the person inside, their watch counts fewer moments. For the one outside, more. That's the bold conclusion. If light does not adapt, time must. Space plays along as well. Distances contract, intervals stretch, and ordinary rules bend to keep light speed universal. We tend to take rulers and clocks as reliable, but under these conditions they cannot stay fixed. They must cooperate with motion and adjust their markings to uphold the constant tempo of light. The walls of reality themselves step in to preserve it. This was nothing short of a revolution. What was assumed to be firm, space and time, lost its certainty. What appeared flexible, the speed of a beam, turned out to be the one true constant. By making that switch, the story of everyday events changes fundamentally. Time was revealed as not one thing for everyone, but many overlapping versions depending on how you move. You can see how this introduces the possibility of time travel into the future. If your watch counts fewer ticks than mine during the same journey, then you are carried forward relative to me. The path you take isn't fictional. It's built into the geometry of motion. Relativity doesn't place time travel in the realm of fairy tales. It sets it firmly inside the calculations. The longer and faster you move, the greater the difference grows. You pass through fewer moments while the rest of the universe marches ahead. In essence, your personal clock drags compared to those back at home. That insight is not just theory. It demands that clocks, once treated as sacred measures, are revealed as negotiable. Two perfectly built devices, started in sync, do not have to remain in sync if they move relative to one another. One runs slow, the other stays ahead. Meeting again, the disagreement is physical and measurable. This means time isn't an outside grid imposed on us, but a quality that bends with motions and mass. That's where relativity moved the conversation. It's worth pausing here. Once you accept time can flow at different rates, a staggering number of consequences follow. What now means for one observer may not be now for another. An event that seems simultaneous to me might not be simultaneous for you. The order of some happenings can differ depending on who watches. That is not carelessness in measurement. It is a built-in feature of how the universe is structured. When synchrony collapses, so does the idea of universal time. What rises in its place is a flexible fabric where speed and gravity decide the tempo. For centuries, engineers and astronomers trusted in absolute time. Rail schedules, celestial predictions, and navigation tables assumed it. Relativity demanded they question even the hands of their chronometers. It predicted measurable changes. If clocks could wander apart based on speed or altitude, then we ought to detect it. Such effects were first slight, but technologies rose with enough precision to check them. The idea stepped from notebooks into hangars, satellites, and laboratories. Over time, careful tests revealed what the equations foretold. Devices in motion tick differently from those at rest. Instruments lifted higher in weaker gravity shift against those closer to Earth. Though tiny in scale, these disagreements are undeniable. Modern technology has to correct for them every second. Without those adjustments, critical systems would drift into chaos. Think of guidance, timing, or navigation. All depend on relativity, not as theory, but as operating instructions. What started as a radical thought experiment has become one of the most used principles in science. The surprise that light could hold constant at all costs reshaped how we see reality. By exchanging absolute time for constant light speed, physics gained coherence, and we gained a key avenue into the future. The whole notion of human time travel begins here, with time bending to protect a beam of light's pace. The thread runs from a stubborn result about motion through Einstein's claim to the devices you carry today. This story is not abstract. It underpins how your phone locates you, how satellites function, and how deep space missions chart their paths. Each relies on the fact that time itself is plastic, not firm. That clocks can move apart depending on their journey. That travel forward, at least, is built into our nature. Once the idea escaped the page, engineers began to look for it everywhere. They strapped clocks to planes, compared signals on spacecraft, and placed experiments on mountaintops. Again and again, the effect appeared. Time is not one universal rhythm. It bends with motion and with gravity's pull. And when we accept that, we step into the real foundation of traveling through time. Now we're ready to see how this wasn't just written down, but actually tested. Evidence came not only from trains of thought, but from aircraft, satellites, and controlled benches in laboratories. What once seemed like an audacious claim has proven measurable 1,000 times over. The world had its proof, and that proof would change how every one of us looks at the ticking of a clock. Racing against the clock in the sky. What would happen if you took a clock, placed it on an airplane, and flew it around the world? It sounds like a question from science fiction, but half a century ago, this test was carried out. To the surprise of many, the clock on the aircraft returned disagreeing with the ones that had stayed home. The difference was not hours, not minutes, not even whole seconds. It was billionths of a second, yet it mattered, because those billionths confirmed that our everyday sense of time was unreliable once it moved at speed or sat at height. To grasp why this test worked, we should note what they flew. These were atomic clocks, precision devices that count the oscillations of atoms. Each tick is a resonance measured in billions per second, steady enough to compare across continents. When several were synchronized on the ground, they matched without waver. But once they were carried aboard commercial aircraft, something strange happened. The clocks no longer stayed in step. When airborne, every clock felt two competing distortions. Speed slows time. This is the effect special relativity predicts: time dilation due to velocity. At the same time, being higher in Earth's gravity changes the pace in the opposite way. In weaker gravity, time runs slightly faster. So the journey was not simple. A clock circling east with Earth's spin lost time. A clock circling west gained time. Both changes arrived exactly as the formula suggested. The scale of these shifts is difficult to imagine. They were measured in tens or hundreds of billionths of a second across entire laps of the Earth. But with atomic oscillators, this was detectable. The pattern was clear. Motion sapped ticks. Altitude added them back. Neither effect was dominant everywhere, yet both played out with predictable results. When scientists compared airborne clocks to those left at a naval observatory, they found the splits lined up with relativity's math. Think of it in simpler terms. Start with two runners at a track. They leave the line together, stride by stride. But if one takes a detour over slightly uneven ground, while the other stays direct, their paces become misaligned. They finish at related, but not identical intervals. In this test, the ground reference clock and the flying timepiece were those runners, and their reunion showed no perfect tie. One had slipped a fraction behind, one had nudged ahead. This was the first time evidence of time's flexibility appeared on a human scale. It had been hinted at in cosmic rays striking Earth's atmosphere and in explosions inside reactors, but never before had ordinary machines we built, carried by us through the sky, proved it so neatly. The message was, Einstein's prediction, once abstract, is alive in our tools. At modest jet speeds, at daily altitudes, we could watch moments drift apart. Why call this decisive? Because it showed that time dilation is not only for particles or black holes. It happens to matter at our own scale, too. Not in decades or centuries of waiting, but in a single trip across oceans. Even in an ordinary passenger cabin, you are experiencing a fraction of it yourself. You may land a billionth of a second younger than a twin who stayed home, though no watch on your wrist can tell. The only reason we can trust it is because atomic clocks are exact enough to reveal what our senses cannot. At first, many dismissed the changes as too small to mean much, but the logic flipped quickly. If the equations matched so well under modest conditions, then those equations must be trusted in harsher ones. If the difference was visible after a single flight, then practical technology had to account for it every day. That realization became unavoidable when another system emerged that depended wholly on timing, positioning satellites. To appreciate the stakes, imagine removing all corrections. A navigation satellite orbits Earth high above with its own atomic clock. Compared to ground timekeepers, its pace differs due to speed and altitude. The result is a drift of many microseconds per day. Translated into distance, that error grows into kilometers. You would tell your GPS to guide you to a street, and it would send you halfway across a city. Your phone would become useless in hours, not weeks. This shows us why those first airborne experiments were not just curiosity. They prepared us for a network of orbiting tools that make everyday life possible. Engineers now program adjustments into satellites to keep them aligned with Earth's time. Computers routinely add and subtract the exact effects Einstein described, or else the positioning system unravels. It is humbling to notice that time's pliability is not buried in equations, but in your daily walk across town. You live without realizing it by constant corrections of relativity. When you check a map, order a ride, or hike a trail, signals reaching your screen have been adjusted against the very drift measured by those flights decades ago. Your device functions only because Einstein was right. So when we ask what happens if you fly with a clock, the answer is profound. You change the outcome of time, slightly, invisibly, but measurably. And because clocks disagree, systems must reconcile them. That reconciliation is the proof that time travel, forward by hair-thin fractions, is woven into motion itself. If you think of the Earth as a stage, then every clock upon it is keeping tempo with the show. But once one of those clocks takes a trip through the air, it plays its notes out of sync. The orchestra no longer has one common beat. It has many, depending on where each instrument has moved. The only reason we enjoy the music without dissonance is because correction sheets keep them aligned. Behind your everyday screen, relativity acts as conductor. None of this bends us back into history. It cannot rewind events or repair mistakes, but it shows we are constantly shifting into different futures, if only by the slimmest counts of atomic oscillations. The experiment did more than verify a claim. It showed time itself was open to engineering. It prepared the way for satellites, travel, and even research into more extreme realms. Each aircraft that lifted those clocks was not doing fantasy. It was writing data into notebooks, carving signatures on charts that showed the pace of time could be altered. For the first time, the theory had touched metal and air and come back with evidence. Once that barrier fell, the debate about relativity's reality ended. What remained was work, applying these truths to systems that could not function without them. Every flight since repeats the lesson at a scale too small for us to notice. Yet the principle is so steady, it cannot be denied. The hands of time are not absolute anchors. They are flexible lines, stretched and compressed by motion and by gravity. The aircraft experiment stands as one of the cleanest points where thought became fact. And as you hold a phone in your hand or follow a car's digital route across a map, you can be certain the software inside corrects for exactly these airborne drifts. Time travel in its smallest form is not a dream. It is an adjustment running quietly in the circuits of your pocket. The next time you decide to locate yourself with GPS, remember that your coordinates are pinned down only because the universe does not keep one common beat. The technology works because clocks in orbit sing a slightly different song and we correct it. You are using time travel without knowing it. Your GPS runs on time travel. Imagine this. You get in your car, open your phone for directions, and the GPS points you not down the street, but miles away in the wrong city. That is exactly what would happen if the satellites above us ignored a rule written into the fabric of nature. Their timing would slip, the signals would mislead, and the map on your screen would dissolve into confusion. The fact that you navigate safely each day is not because GPS escaped these problems, but because it learned to live with them. High over our heads, satellites circle Earth in steady arcs. Each one carries an atomic clock, devices tuned to a precision of billionths of a second. They travel at astonishing speed, over 14,000 kilometers per hour, and they orbit at heights where gravity's grip has slackened. Both of those conditions reshape how clocks behave. Back on the ground, our watches tick away at a different rhythm. Move them into orbit, and the rhythm shifts. One slows because of speed, the other speeds up because the pull of Earth is weaker. The two influences stack together, and the result is a disconnect between sky and ground. If nothing were done, the effect would grow larger every day. The misalignment is on the order of tens of microseconds each day. That sounds invisible, but when you remember that light itself moves about 300 meters in a microsecond, you can see the danger. Within hours, your location would creep off. Within a single day, the drift would add up to nearly 10 kilometers. Following your GPS to the store, you would find yourself standing at the wrong building. Driving on a highway, you might be told to turn when no road is there. The map system would collapse. The analogy is simple to grasp. Picture holding a paper map with neat lines marking streets. Every hour those lines slide slightly, drifting off the page. At first it looks close enough, but by the end of the day, intersections no longer match reality. You could not orient yourself. That is what uncorrected satellite clocks would do to your navigation. The universe itself is trying to drag the system out of sync. Without help, it fails. So engineers apply Einstein's fixes right into the code. When a signal leaves a satellite, its timestamp carries hidden adjustments that account for speed and altitude. The receivers on Earth are built to expect those adjusted stamps. They compare time differences from several satellites, and from those differences, they calculate your position. Because the corrections are continuous, your phone sees distances accurate to within a few meters. When you follow that glowing blue dot, you are trusting relativity. The remarkable part is how invisible it feels. You ask the system for directions to a coffee shop, and you arrive. You do not notice that without relativistic corrections, you could be left wandering in the wrong part of town. This is not theory waiting for a future test. It is infrastructure running quietly in orbit. Each day, billions of people lean on it, and each day, it works only because Einstein's equations are written into the system's software. It is tempting to think of time travel as fiction involving exotic machines. Yet here we have proof that your own daily life depends on time running at different rates and being corrected back into harmony. When those satellites tick more quickly than our ground clocks, they have stepped into a slightly different future. That difference is shaved off, tamed, and then handed to your screen as coordinates you trust. You are not aware of it, but you rely on a form of time travel every time you check a map. Think of a symphony orchestra placed in scattered halls. One section sits in a stadium downtown, another miles away on a mountain. Each set of musicians plays their part, but the sound arrives at different moments. If you want music, you must correct for those delays and distortions, lining every instrument into one rhythm. That is what GPS does. It takes a scattered constellation of clocks, each touched by speed and gravity, and it lines them up again so you can hear the right tune. This story matters because it makes relativity tangible. When Einstein proposed these effects, they seemed abstract thought experiments. Now we see them pulsing in signals that keep planes on path, ships off reef, and traffic guided through cities. Without corrections, airliners would miss runways, supply chains would break down, and even the global power grid would struggle to stay synchronized. The stability of our machines requires relativity not as an idea, but as a rule built into the operating manual. You may wonder why gravity pushes time one way and speed pushes it the other. Speed slows a clock down because rapid motion stretches the path of light inside it. The beams must cover more distance, so time itself ticks slower to keep the speed of light unchanged. But at altitude, where gravity's tug is weaker, the opposite happens. A clock runs faster, as though freed from the heaviness pulling on its pulses. Satellites live in both conditions at once. The balance tips in favor of gravity's effect. So orbiting clocks end up faster than ours, and engineers must slow their signals. Without this tidy blend of physics and engineering, the network would wither. In practice, each clock is tuned before launch to run at a slightly off pace, so that once in orbit, it aligns with ground time. The corrections continue as long as the system operates. It is time travel, not science fiction, but scaffolding that holds our world together. Now pause on that. Your location on Earth is fixed only because the universe's distortions are corrected each second. The satellites above you are constantly slipping through moments faster than you are. The system, at heart, is a machine that compares many small instances of time travel and then cancels them out to find your place. This is not about far-off futures. It is proof that traveling at different rates through time is part of the machinery of the world. What keeps your screen accurate is the daily bending of seconds. What rescues precision from chaos is our ability to correct it. Once you see that, the leap to larger scale ideas becomes smoother. Time dilation is not speculation. It is already part of the skeleton of modern civilization. So if we build entire systems on these tiny divergences of time, what happens when we face them at greater magnitudes? If satellites, moving at speeds far less than light, already live different seconds, then what if machines push close to that ultimate limit? What would time look like on board, and what would it look like for us left here on Earth? The same principle applies. Increase speed toward the speed of light, and the drift between two clocks explodes into years, centuries, even millennia. The calculation is clear. We accept small adjustments today, but the framework hints at much larger journeys. So the next time that glowing map points you to a door, and you arrive without error, remember the hidden truth. Your GPS only works because time has already been bent and corrected. It is not fantasy or theory. It is the reason your world is navigable. And now, building on that knowledge, we can ask something more ambitious. If time dilation at satellite speed already changes reality, what would happen if we pushed nearer to light itself? That takes us to the idea of near-light speed journeys, where a person could leap forward across centuries while experiencing only a handful of years. If you could ride a beam of light, what if 10 years of your life meant thousands of years for everyone else on Earth? That is the strange outcome written into the rules of relativity once you press toward light speed. It changes what speed means. In daily life, we treat motion as just distance divided by time. Run faster, drive quicker, fly higher. Everything is a straight trade of distance against hours. But when you draw near the cosmic limit of light, that simple picture breaks. Speed eats not just distance, it slices into time itself. Here is how the effect grows. At modest velocities like planes or satellites, time dilation is minuscule. We measure the changes in billionths of seconds, but relativity says the impact rises exponentially with speed. Add another 9 in the decimal places, 99.9% of light's pace, then 99.99, and so on. And suddenly the shift is immense. You could climb into a vessel, accelerate almost to the speed of light, and live 10 normal years by your clock, only to return and find Earth thousands of years older. The more digits you add, the stranger it becomes. This is not speculation. The math has a name, the Lorentz factor. It tells us exactly how much slower time runs for motion near light speed. The formula grows steep as the velocity nears that absolute wall. If you draw its curve, it rockets upward, making normal time impossible to maintain. For you, each day clicks softly forward. For home, generations would pass into myth. Think of the classic twin story. One remains on Earth, the other departs on a journey almost at light speed. Years later, the traveler returns youth still in their body, while their sibling has aged far beyond recall. It is not trickery. The moving twins' clock lagged because motion elongated the path light traveled inside every process, inside their heartbeat, their cells, their thoughts. Each tick was slower relative to Earth. That's why time itself ran on separate routes. You can bring it down with a vivid image. Picture falling asleep in the quiet of your cabin. 10 years go by. You wake, stretch, step out, and discover entire civilizations have risen and fallen on the planet you left behind. For you, it was only a nap and a decade. For Earth, it was an epoch. Relativity makes this more than a bedtime story. It is the cold outcome of the mathematics that define our universe. Such journeys are one-way trips into the far future. They are personal machines for leaping forward in time. Once you accelerate and maintain such speed, your aging slows compared to the rest of the cosmos. You cannot prevent Earth from running ahead. You can only accept that if you climb back down from the voyage, you step into a world far beyond your memory. Time travel into the future is not forbidden in physics. It is encouraged by the very rules of motion. But there is the obstacle that stops us: energy. The closer you drive a massive object, like a craft filled with people, toward light's pace, the more its effective mass increases. Small increments in speed demand ever larger bursts of energy. It is like trying to push a boulder up a hill that grows steeper every step. Near the peak, the slope is almost vertical. The energy requirements stretch to absurd scales. Even the most powerful machines we have today, colliders buried underground, strain to accelerate single particles to those speeds. They use megawatts of power just to nudge quarks and protons against their barriers. Scaling that up to a starship with crew and shielding leaps beyond any known technology. So, at our size, this kind of travel isn't just hard, it is practically impossible. You would need fuel equal to the output of stars and engineering far sturdier than anything our materials can handle. Exposure to radiation, dust impacts at such velocities, and simple structural stress would tear a vessel apart. Physics says yes to the principle. Engineering says not yet, with a weight Earth cannot overcome. Still, the idea is anchored because we already watch it unfold every day at small scales. Subatomic particles born high in the atmosphere live longer than they should because their immense velocities stretch their lifetimes. Neutrons, muons, and others survive the fall to Earth thanks to time dilation. They are existing proof that this bizarre shifting of aging is not fiction. We study it in detectors. We even rely on it for experimental design. For them, near-light motion pushes their brief existence farther into time than would ever be possible at rest. This, then, sets our imagination moving. If particles can dance briefly into the future with each rush near light, perhaps one day we could too. The barrier is brutal, but the framework is sound. The rule is physics, not wish. Here's another way to think of it. Imagine a river where you row across with increasing speed. Normally the crossing takes 10 minutes, no matter how hard you row. Now imagine that each time you double your strokes, the far shore is swept downstream exponentially faster. Soon you row 10 minutes, but the bank you left has been carried kilometers away. Row another 10 minutes, and the bank has drifted past the horizon. You row hard, but the cost of crossing grows infinitely steep. That is how time behaves as you approach light. It forces us to redefine speed as something far richer than meters per second. At extremes, speed isn't about getting somewhere quicker. It's about changing how long existence itself takes. It carves a new path through years and centuries. We are not used to thinking of motion as rewriting life, but that is what relativity ensures. So from the twin paradox to the math on blackboards, all signs point the same way. Future travel is embedded in the structure of reality. The gap between what your body feels and what the rest of the cosmos experiences is where the future opens. Right now, only particles exploit it. But we can imagine the trajectory. If engineering ever learns to tame raw energy at scales inconceivable to us, the physics will support human steps into far futures. For now, it remains an illustration of what is possible rather than a plan. The dreams are slowed not by doubt, but by power requirements. To lift a spacecraft and push it into a fraction shy of light would cost more energy than our planet harnesses. Each decimal further into the 99.9999% demands leaps greater still. That is the asymptote we face. And so at this moment, the largest accelerators on Earth remain our only window into this future. They cannot move ships, but they do push protons with enough momentum to stretch their lifetimes. Each time those machines fire, they are staging a small test of what human-scale voyages cannot yet achieve. Those beams of particles are our mayflies riding on near beams of light. Which brings us to our next stop. If we want to see this form of time travel not as dream, but as daily experiment, we look underground to the colossal ring that hurls particles into tomorrow, the world's biggest accelerator. The machine that launches particles into tomorrow. Buried beneath the countryside in Europe sits a ring of machinery so large it forms a loop 27 kilometers around. It is made of magnets, pipes, sensors, and steel, hidden deep under the ground. There, scientists do something remarkable. They push protons until they fly at a pace so close to light that the difference is measured only in fractions beyond most instruments. When those protons smash into one another, fragments spray out, giving glimpses of the building blocks of nature. But one of the side effects is even stranger. Particles that should vanish in the blink of an eye last far longer than their natural lifetime. It is as if the flow of their own clocks has been stretched, allowing them borrowed moments that would otherwise never exist. This machine is the Large Hadron Collider. It does not look like what you might imagine. Rather than a glowing tunnel of fiction, it is a set of nested pipes kept near absolute zero in temperature, all to keep the beam straight and steady at unimaginable speed. Protons cycle around that loop thousands of times a second, pulled by magnets that bend them again and again. The aim is to recreate the conditions that existed after the first second of the universe, close to when energy first crystallized into matter. But even before those head-on collisions, one effect is already present. The rules of time itself shift for every particle in the ring. To understand why this happens, focus on the particles called muons. At rest, they vanish in about 2/10,000,000ths of a second. That is their expected life, a timer built into their nature. If you could trap muons and watch them, you would see the stream of them fade almost instantly. But push muons near light speed, and that clock refuses to keep its normal tempo. To outside eyes, their decay is slower. Where we expect them to vanish in microseconds, they last many times longer. They stretch far past their natural span because their moving frame carries them through time differently than ours. In ordinary words, this means the muon survives into its own future. The muon has not changed its script. Its inner processes keep following the same rules inside its frame. But compared to us, the cadence is drawn out. What should be over is not yet over. The muon has traveled forward relative to our clocks simply by moving quickly. Time passed more slowly for it than for us, so its life gained surplus duration in our measure. An analogy helps. Imagine a mayfly, one of those insects born with only a day to live. At rest, the mayfly's life is short, hours and nothing more. Now imagine if flight near light speed expanded that life. Instead of fading at sunset, the mayfly glides through several dawns before its end. To us, it appears to have stretched its brief gift into days. The mayfly experiences no difference, but our record of its existence is elongated. That is what happens to muons and other unstable particles in an accelerator. This is moving matter into the future, not by minutes or days, but by fractions that add up to entire expansions of lifetime. This is not fiction. This is recorded in data whenever the collider operates. Physicists expect it, measure it, and calibrate machines around it. It is so common that, without accounting for time dilation, the predictions and output of these experiments would be ruined. On subatomic scales, traveling forward in time is part of the landscape of modern research. Think about what this means. Every time beams rush around that ring, thousands of particles already step into tomorrow compared with us. They carry on longer, live past their limits, and die later than natural law would have allowed without motion. This repeats billions of times as collisions spill across detectors. What once felt like a dream is instead routine. Time travel is triggered whenever particles are accelerated at high speed. If this is true at small scales, why not at human scale? The answer is energy. The collider is already one of the largest power-hungry science machines on Earth. Keeping beams at near light speed demands staggering energy, and that is for subatomic matter. To move a person or an entire ship with that same factor of dilation would require energy beyond what our planet can harness. Mass rises with speed, push faster, and each fraction closer to light demands more power than before, an endless climb, steeper at every step. A beam of protons can be coaxed up, but a spacecraft would be too demanding. This barrier does not cancel the principle. It only places it beyond reach today. For small particles, time dilation is a tool used in experiments. For large objects like us, it is a dream. The divide is not physics, but power. Our engines, fuels, and materials cannot reach the scale required. That is why the best evidence comes not from ships sailing the cosmos, but from accelerators hidden in tunnels. When you consider this, time dilation stands out as both ordinary and profound. Ordinary because it is measured so often. Profound because it shows what reality allows if circumstances expand. It means that tomorrow is not locked to one pace. It also shows that length of time is not a given, but flexible depending on path and speed. Always the light speed barrier frames it. Always the dilation arrives as the frame grows fast. A particle lasting longer because it races in a ring is not a matter of perception. It changes data we record, footprints on detectors, signals on screens. It is more real than any theory can be, and that reliability shows us that traveling to the future is not an open question. It is a working fact, played out many times a second, under our world. The collider turns out to be our machine to move matter into stretched time. In the same sense that a telescope brings distant galaxies into focus, this ring brings forward what happens when relativity becomes extreme. The mayfly lives longer. The muon lingers. Matter outruns natural decay. That is travel into tomorrow. For now, the effect stays locked to the small. Energy imposes a wall on larger scales, but by watching these beams and fragments, we learn what motion can do. We learn that the universe bends clocks to hold the speed of light firm, and we learn that time travel forward is nothing strange. It is the daily result of how reality holds itself together. The true question, then, is not whether we can go forward. That is settled. The question that remains is harder. Can we ever reverse the path, step into yesterday, and undo what has happened? The collider cannot answer that, and so attention must turn to the other side of time, the lure of going backward. The impossible temptation, backwards in time. Could we undo a mistake by turning the cosmic clock back? The idea clings to us because in daily life, time feels like a straight line, birth, growth, decay, and once an event has passed, it seems locked. Yet the equations we use to describe space and gravity leave room for stranger shapes. In some solutions, time is not a line, it is a loop. Follow the path in a certain way, and it can bend back to meet itself, carrying anything along for the ride. These closed, time-like curves are what the math of relativity permits, even if reality itself resists letting them exist. General relativity describes space-time not as a background stage, but as a fabric that can warp, twist, and curve. Within certain extreme conditions, close to rotating black holes or hypothetical cosmic strings, the geometry folds in on itself in such a way that the future can meet the past. If you could steer through one of those loops, the equations say you might return to a point you had already left. In theory, that means visiting yesterday. In practice, it means stepping into trouble, because the past is not an empty room. It is filled with causes that lead forward. If you intrude there, the chain can tangle. The most famous problem goes by a simple name, the grandfather paradox. If you travel into the past and prevent your ancestors' life, you prevent your own birth. But if you are never born, you cannot travel into the past to interfere. Cause and effect chase each other in a circle, and the logic collapses. Another version, more subtle, is the bootstrap paradox. Here the loop contains information or objects without origin. Imagine bringing back a page of equations from the future and handing it to someone in the past. That page becomes the basis of discoveries that, centuries later, are compiled as the page you first carried. Where, then, did the content come from? The loop has no source. The information exists without beginning. This is not just puzzling. It undermines the principle that effects must flow from causes. It leaves a universe where some things exist untethered to any origin. Paradoxes like these are not forced into relativity's equations. They fall out naturally once curves that bend back in time are allowed, and they raise not only logical snags, but physical ones. A universe that lets its past be altered risks tearing the very notion of causality apart. Everyday consistency, the idea that events happen in order, would evaporate. You could meet outcomes before their causes. You might encounter explanations that never had a beginning. The stability of history would lose anchor. This tension shows why traveling forward in time is accepted physics, while traveling backward remains doubtful. Moving to the future simply means your clock disagrees with others, and this we already measure scientifically. But moving back invites contradictions, loops, and self-destruction. If the future is rubber, the past is glass. Try to press in the wrong direction, and something must break. An analogy helps make sense of the conflict. Picture holding a finished novel. Once you reach the end, you may wish you could flip back and edit the first chapter. In your hands, the book is complete. Altering Chapter 1 would scramble every later page for consistency. Characters introduced midway would appear before they were written. References would point to words that no longer exist. The narrative would collapse under contradictions. That is what revisiting the past would risk, rewriting causes after effects are in place. To avoid this chaos, Some physicists argue that nature carries hidden safeguards. One suggestion bears a striking name: chronology protection. It proposes that while equations may sketch time loops, real processes step in to destroy them before they function. Quantum fluctuations, exotic instabilities, or the collapse of matter might erupt whenever a closed time-like curve tries to form. What results is a universe that protects its timeline, blocking opportunities for paradox. In this view, history is self-defending. This does not end the fascination, though. The very fact that equations allow such curves is tantalizing. It suggests that mathematics is ahead of experiment, pointing to territories of space-time we cannot yet test. Could exotic matter with negative energy hold a wormhole open long enough to form a loop? Could cosmic strings, if they exist, bend space-time tightly enough to curl time? These remain open questions, pushed aside by practical limits. Enormous energies are needed, and such structures have never been shown to be stable. But the possibility, written in the symbols of relativity, keeps the idea alive. If backward travel is forbidden, the reason might trace to entropy. Our universe contains an arrow of time driven by the second law of thermodynamics. Disorder grows in closed systems. Glass shatters, heat spreads, stars burn out. To reverse time would mean reversing entropy, and we never see that happen on a global scale. The arrow always points one way, from order to disorder. Allowing a loop to the past would overturn that basic tendency. It may be that physics simply cannot roll against this slope, so the situation is this. Travel forward is consistent, measured, and usable. Travel backward is a web of paradox we cannot cut through. Space-time's math entertains strange loops, but their physical reality may be impossible. If you dream of visiting yesterday, physics is silent or hostile. What keeps stability is the refusal of the past to bend. And yet, curiosity remains. Because at the smallest scales, in the murmur of quantum experiments, time does not always look so rigid. When researchers test whether choices made now influence outcomes already recorded, the results appear slippery. At subatomic scales, the order of cause and effect strains. If the macroscopic past resists, the microscopic world sometimes hints at a different story, which brings us to the frontier of experiments where photons, detectors, and choice itself press on the nature of time. The grand paradoxes play out in thought, but in the quantum world we see whispers of flexibility. That is where modern physics turns its eyes, to ask whether time at its core plays by gentler, less rigid rules. Quantum whispers about time. What if your decision now could ripple backward and change the outcome of something that has already happened? At first, this sounds impossible. We are used to time pushing forward, cause first and effect second. Yet, at microscopic scales, physics sometimes whispers a different story. The boundary between past and present, so clear in daily life, blurs when you carefully test the behavior of individual particles. In a family of tests known as delayed choice experiments, light or matter seems to decide how it behaved earlier only after a scientist chooses how to measure it later. A particle starts on its path, and only once it has passed a fork in the road does the observer decide whether to check one property or another. Strangely, results show the choice of measurement appears to shape how the particle acted at the earlier point. It is as though the present stretches back and molds the past track. To our everyday sense of order, this is deeply unsettling. This suggests causality may not be ironclad. In mathematics, the rules of quantum mechanics allow many possible paths at once, until measurement forces one to be recorded. If that measurement comes later, then what we mark as the past was not settled until the present. That sounds less like a steady line of events and more like a flexible script, rewritten as the story is read. The difference with ordinary life could not be sharper. In classical physics, initial states always fix results. In these quantum cases, results open space backward as well. One of the clearest examples comes from photons. A beam of light is sent toward a detector. On the way, the path can either be treated as if the photon were a wave or as if it were a particle. If you choose one type of test, the photon's earlier behavior aligns with that. But if you choose the other test, its earlier behavior aligns with the alternative. The action in the present selects the form of the past. The photon obeys a rule that makes no sense in daily human experience, yet the statistics across many trials confirm it with precision. Here the analogy of a mystery novel helps. Imagine flipping to the last page before you read the middle. When you glance at the ending, it not only reveals what happened, it rewrites the sections before it. Characters act in line with what the ending demands, not what was originally written. To us, a book cannot behave this way, but quantum experiments hint the universe sometimes does. The ending adjusts the middle. The future shapes the past. Now add entanglement. When two particles are entangled, they share one fate across distance. Measure one, and the other responds instantly, whether centimeters apart or light years. The oddity deepens because the order of these two measurements is not always clear. Depending on perspective or motion, one event can come before or after the other. And yet both particles present matching results. This collapses our normal arrow of time. For them, what matters is correlation, not sequence. They exchange consistency outside our usual cause and effect order. Entanglement suggests that time ordering may not be absolute. What comes first and what comes after is partly a matter of perspective. For the particles, outcomes simply match, with or without clear sequence. In daily life, that would be like two dice thrown miles apart, always landing on the same number, even if no one agrees who threw theirs first. The synchrony exists outside linear order. At the quantum level, then, time seems elastic. It can bend, merge, or stutter in ways very unlike the smooth curves of relativity. Relativity bends time with speed and gravity. Quantum mechanics twists it with choice and entanglement. In one world we measure dilation, in the other we see retroactive adjustment. Put together, they suggest time has layers, scales, and perhaps hidden rules we do not yet grasp. Of course, physicists argue about how to read these experiments. One camp says nothing in the past changes. Instead, the results are produced as correlations that only look retroactive. The particle never decided earlier. The choice in the present simply determines which part of a broader reality we access. Others argue the retroactive picture may be real. The future could indeed influence the past. At this stage, both sides hold ground because the data fit both frames. The debate is not about results, they are known, but about interpretation. For us, the lesson is clear. At small scales, time runs less like a strict arrow and more like a web. Effects weave into causes, and the order is not always stable. That does not mean we change yesterday's weather with today's choice, but it does mean our picture of time as strict flow falls short of completeness. It matters because we dream of time travel. If laws at one level allow even tiny loops, then any full picture of the universe must explain where those loops end. At a macro scale, history is stable. No paradoxes, no vanishing ancestors. At the micro scale, uncertainty reigns. So the open question is how one blends into the other. Why does the subatomic world allow whispers of retrocausality while the human world stands rigid? Perhaps there is a transition point, a scale at which disorder and decoherence iron out temporal flexibility into our familiar arrow. Perhaps not. For now, what experiments give us is awe more than answers. When a detector click seems to rewrite what a particle did seconds before, we are forced to admit our intuitions about time may be incomplete. A law may stand strong in one regime, but give way in another. Relativity and quantum mechanics each demand respect, even if their stories of time do not align. We cannot yet build a machine that uses entanglement to undo events or delayed choice to step back into last week. The systems that show these effects are fragile, fleeting, and isolated. The moment they scale up, the subtle quantum options collapse. What remains is the one-directional march of thermodynamics. Heat spreads, entropy grows, and life moves forward. That is why our bodies, our histories, and our daily clocks obey the familiar flow. But the whispers remain. At subatomic scales, the universe hints that causality is not as strict as we once believed. Your imagination may pause here. If the present can reach backward in quantum events, and entanglement can blur sequence entirely, then perhaps our definition of past and future is incomplete. That recognition alone changes how you see the ticking clock on your wall. The quantum world tells us that while the macroscopic past seems safe from paradox, the microscopic rules are not simple. And as researchers push deeper, the line between cause and effect may reveal seams we never guessed. Each new test adds puzzle pieces to a picture we are still trying to fit. And that picture leads to a natural question. If time flexes at these scales, what does that mean for physics as a whole? And where does research head next? The future of our relationship with time. If time travel is possible in one direction, who will harness it first? That is not just a science question, but one tied to power, resources, and control. Because the future is already open to us in principle. Motion slows clocks, gravity bends seconds, and satellites prove it every day. But harnessing that effect beyond fractions of a second, shaping it into a usable tool, is the frontier of physics now. Whoever finds a method to do it would guide not only research, but humanity's shared future itself. Researchers are beginning to suspect that space-time may have more structure than we see. Our daily lives take place inside 3 dimensions of space and a single dimension of time, yet theories suggest there may be deeper layers hidden from view. One of the most ambitious frameworks is string theory. In its description, particles are not tiny dots but vibrating strands. Those strands vibrate in ways that require extra spatial dimensions. The claim is bold. If reality includes more dimensions than we perceive, then time may behave differently when those layers are accounted for. Time could turn out to be a slice of something bigger, not the whole. What we measure as steady seconds may be shadows of activity in hidden realms. Another line of thought is the holographic principle. This idea suggests that all the information inside a region of space-time could be encoded on its boundary, just as a flat hologram encodes a 3-dimensional image. If this principle holds, then our sense of moving through time within a volume of space might be reconstructed from data painted onto a distant surface. That flips our intuition. It means the flow of time we experience is emergent, not fundamental. The sliding of moments might be the way underlying rules manifest to us, not the rules themselves. And if something is emergent, in theory it can be adjusted, redirected, or even engineered. Then there is quantum gravity. At the smallest scales, space-time itself may not be smooth. Instead, it could be granular, like foam under a microscope. If time is woven together particle by particle or unit by unit, then its flow might depend on patterns we do not yet control. The search for quantum gravity is not just about unifying forces. It is about whether space-time itself can be manipulated like matter or energy. If those building blocks are discovered, the door to time control opens wider than before. But there is tension at every step. If breakthroughs confirm these hidden layers, then time engineering might move from imagination into planning. Yet the same work could reveal that limits are permanent. We may learn that geometry or entropy creates boundaries impossible to cross. The equations might insist the past is locked forever, or that the energy required to stretch future travel beyond what particles already show is unreachable. Either conclusion reshapes our sense of possibility. Both are valuable, but they point in opposite directions, endless horizons versus hard walls. At this stage, progress is measured less in engines and more in chalk lines and qubits. Equations explored across string models, holographic setups, and quantum experiments hint at consistent patterns, but none yet unifies into a single law. Technology follows theory slowly. For example, work on quantum computers is partly about processing these strange rules in controlled form. But the machines are fragile, and their scale is modest compared to the continents and stars involved in time dilation. The present tension lies here. Theory has grown vast, while technology remains young. Still, the future of our relationship with time does not stand still on paper. Time dilation has already changed navigation networks and research into cosmic particles. The same rule stretched further could change space travel itself. A craft coaxed into higher relativistic speeds would spare its crew years, but burn centuries outside. Communication lags would appear. Nations would face travelers aged minutes who returned to lands transformed, and human presence in the stars would begin under a rhythm shifted from Earth. The difference is not theory, it is cost. Energy is the barrier. Small accelerators drain whole cities' worth of power simply to stretch particle lifetimes. Scaling up to macroscopic travelers would demand outputs larger than planets currently manage. At what energy cost could a crew leap decades or centuries? That is the real question. Experiments say yes in principle. Engineering says how and at what cost. If that cost is ever met, the consequences stretch beyond technology. The one who holds such control would in practice hold access to the future. They could transport information forward, shelter explorers from the weight of centuries, or perhaps shield entire communities. Such control could also be abused. A gap in available futures could widen inequalities. A society able to fast forward its own development might leave others permanently behind. The stakes are not only scientific but political, even ethical. To control time is to control history's rate of change. It may help to think of it as controlling a dam. Water flows downhill whether we like it or not, but those who build a dam can stop, redirect, or release it in chosen ways. The arrow of time, like water, points forward. But with enough energy and the right design, engineers might step in to change the pace. Just as control of rivers set the path for cities, Control of time's flow could set the path for civilization. This is why research into string vibrations, holographic surfaces, and discrete spacetime is more than academic. It is preparation for choices that may one day arrive. If the hints are correct, we may not be asking whether travel forward is possible. We may be asking what price we are willing to pay and who decides it. Right now, progress is humble but crucial. Precision experiments test whether tiny disturbances match predictions from candidate theories. Simulations push to see if information on surfaces truly maps volumes, or if string vibrations describe particle families we observe. Each confirmation tightens the map. Each failure shuts down false roots. The future of our relationship with time is being refined, one calculation and one test at a time. So when we hear the words time travel, we should not think only of fantasy machines. We should think of laboratories where clocks are compared at different heights, particle beams stretch living seconds, and quantum experiments confuse cause with effect. We should think of theorists trying to write one consistent script where relativity and quantum rules share a stage. That work is happening, and it tells us the timeline is still under construction. The small payoff today is knowing the question has shifted. Not if, but how. And not only how, but how much energy and who pays the cost. The problem is practical now, not mythical. And the prize is extraordinary. Whoever cracks the challenge will control humanity's access to tomorrow. But before we finish, pause to consider what lesson we already have in hand. Time may be flexible, it may be layered, and it may be open to engineering. Yet even without control of hidden strings or holographic maps, the everyday truth is striking. We are already moving through time at variable rates, our devices already correcting those drifts, our experiments already measuring tomorrow in muons and particles. Which brings us to the final reflection, the question not of how we escape time, but what time travel really means for us today. Time is not rigid. It bends and stretches, it speeds and slows, depending on motion and gravity. That is the core truth that Einstein's work revealed, and modern experiments prove it every day. In that sense, we are all time travelers already. Each step forward is a drift into the future, and even tiny changes in speed or height alter how fast our clocks run compared to others. So perhaps the goal is not to escape time at all. The greater journey is to understand it, and by understanding, decide how we use the moments we are given.